Alright, in this video I want to look at what's called the second fundamental theorem of calculus, or the second part to the fundamental theorem of calculus. We're going to explore I'm going to do three little examples up here. We're going to take a look at each of them. So here's our first one. We're going to take the integral of 3x squared. And instead of just doing the integral, I want to take it a little bit further. I want to take the derivative of this integral. And I want to see what happens. So as we look at this, let's do the inside first, and we'll worry about the derivative later. As we take the integral of this, we end up getting x cubed plus c. This is an indefinite integral, so it's an equation, so we got the plus c. Then we're going to take the derivative of that. So the derivative of this, the derivative of x cubed, is going to be 3x squared times the derivative of x, which is just 1, plus the derivative of a constant with respect to x is going to be 0. So we end up getting 3x squared. And you might look at that and say, well, that's just silly. All we just did was just these undid each other, which is exactly what they do. We end up with this original function that we started out with. Right? That guy ends up being our answer. Okay. Let's take a look at let's just change one little thing. So I still want to take the derivative of an integral. It's still going to be 3x squared. This time I want to add bounds. So what if I made the bounds, let's just do 1 to 2. So let's do the same thing. So I'm going to find the antiderivative of this, which I already know to be x cubed. I don't need the plus c because this is a definite integral. If I did, and it's just fine if you do, plus c, that's fine. But I do want to evaluate this from 1 to 2. And then I'm going to take the derivative of it when I get finished evaluating it. So I'm going to have the derivative of x cubed. Well, I'm going to plug in 2, so this is going to be 2 cubed plus c minus, plug in 1 cubed plus c. Let's simplify that up a little bit. We get the derivative of 2 cubed is 8 plus c. 1 plus c, this is going to be 1 plus c, just pull in the minus sign, or factor, distribute the minus sign, we get minus 1 minus c. The c's cancel out, which is why earlier I said you didn't need to have, since it's a definite integral, you don't really need to put the plus c because it's always going to cancel out. And we end up with the derivative of 8 minus 1, which is 7. And the derivative of a constant is simply 0. So that would be my answer here. Now I hope you could look at both of these and you would say, yeah, that makes sense. If I'm taking an indefinite integral of any equation, doesn't matter which one, if I find that antiderivative and then take the derivative of it, I should get back to that same exact equation that I started out with, my integrand in my integral right here. Likewise, if you take any definite integral with constant values as the bounds, your answer to a definite integral with constant bounds is always going to be a number. So this case, it happened to be 7. It could happen to be something else later on, but it's always just going to be a number. And when we take a derivative of that number, or that derivative of that constant, we're always going to end up getting 0. Well, I'm going to do one more, but we're going to change something. We're going to take the derivative of 3x squared dx, okay? But this time, instead of having constant bounds, I'm still going to keep the 1 as a constant bound, that's fine. But the upper bound, instead of having it be 2, I'm going to actually have it be an equation. I actually have a variable in it. So I'm going to do, let's do x squared. Now let's do x cubed. And then let's try this one. So let's take the antiderivative of this. We get the derivative of, it's still going to be x cubed. We get plus c. We don't need the plus c because it's a definite integral. So evaluated from 1 to x cubed. Oh yeah, that's kind of fun. Then we are going to evaluate this. We still have the derivative out here that we'll worry about in a second. So I've got x cubed minus 1 cubed, or just 1 cubed. There we go. So x cubed This becomes, in fact, I'm just going to leave it. This is going to sound a little silly at first, but I'm just going to leave it like it is. X cubed, I'm not going to simplify it yet. Cubed minus, I'll simplify this, minus 1. Okay? Now let's take the derivative. So as I take the derivative of this is going to be a power rule problem. I'm going to ignore the inside for a second. I'm going to bring the 3 down out in front. So I've got 3, leave the inside alone, and lower the exponent by 1, so it becomes a 2. Then times it by the derivative of the inside. So the derivative of the inside is 3x squared. And then the derivative of negative 1 is simply 0. So this ends up being my final answer. So notice it's not what I started out with. If you notice, this equation that I have right here is not exactly what I started out with up here. So it's not quite like this first one. And also the answer is not 0, so it's not like this one. So having that variable in the bounds does make a difference. Now the question is, how do we go from here to here without having to do all these steps? Now there's nothing wrong with doing those steps, right? But what if I had another problem? I'm going to erase all this stuff over here. Okay, so let's do another one. Where's my pen? There she is. All right, so let's take the derivative of the integral. Let's, instead of doing 3x squared, we'll try a different one. Let's do e to the t squared dt. All right, and let's still have our bounds be, we'll go from 1, we'll just do the same thing we did over here, 1 to, actually we'll do x cubed. Nothing wrong with that, x cubed. Okay, now I do have to make one little quick note about this over here. That actually is really bad. That's actually bad notation. When you have a variable in the bound, I forgot to mention this, but if you have a variable in the bounds, it should not be the same variable you have in here. So even if I did start out with a 3x squared, I probably should have changed this to something else, like a t. And it doesn't really do anything. It's just a notation thing to have the whatever variable you have in your bounds be different than what you have down here. So I probably should have changed those to a t instead. It's not a big deal though. You still get the same answer in the end because right here this is going to be a t, right? So I'll plug in x cubed 4t and end up getting this. So everything else works out the same. So I've done that over here. So I've got t's instead of x's. All right. So now if you look at this one, if we try doing the same thing, I would first look at this and say, okay, what's the antiderivative of this? And I'd say to myself, gosh, I don't know. So I might think, oh, I'll use U-Substitution because that's the method we've learned to solve these more complex integrals. Well, if I set my u equal to, say, t squared, take the derivative with respect to u, I guess I'm doing it with respect to t, sorry, du with respect to t, and I get 2t, okay? Now, if you think ahead just a little bit, when I try doing the substitution part, I'm not going to have anything to substitute my du in for. My t squared right here is going to get changed to u's, and I don't have a t anywhere in there to substitute for. So we have not learned how to take the antiderivative of this equation. So if I don't know how to do the antiderivative, I can't get down to this step right here. Well, this is where the second fundamental theorem of calculus comes into play. And let me show you the actual answer to this problem. Let me erase this, this U-substitution work right here. The answer to this equation right here is going to end up, after you do the integral and take the derivative, so after you've done all that stuff, it is going to end up being e to the x cubed squared times 3x squared. That is what this is going to end up simplifying down to be. Now I just skipped all of this stuff right here. So let me show you the second fundamental theorem of calculus and show you how it works for both of these problems. If I am taking the derivative, I'm going to write it down here. If I'm going to take the derivative of some integral, we'll call it function f, the integrand f, so f of t dt. And I have bounds. I'm going to call this one u, I'm going to call this one v. All right? So if I want to take the derivative of this integral, well, as we try solving this, we find the antiderivative of f, which I'm going to use capital F to represent that. Okay, so capital F of t. evaluated from u to v. Okay, and that gives us, I'm plugging the top bound first, f of v minus f of u. All right. Now, I guess I forgot my derivative sign, so really there's a, this is in, that was really poorly done. There. Let's try that again. So I've got this in, brackets or whatever. There is a derivative out here. We have not done that yet, so I got to make sure I haven't said that I've done it yet. Okay, d over dx. Well, let's take the derivative of this now. The derivative of capital F is going to be lowercase f. Since the antiderivative of lowercase f gave me capital F, the derivative of capital F is going to give me lowercase f. So lowercase f, leave the inside just the way it is, right? So that's going to be v times by the derivative of the inside, v prime, minus little f of u times the derivative inside, u prime. And this down here is the second part of the fundamental theorem of calculus. If I am taking the derivative of an integral and it has variables in its bounds, then this is how I can figure out what that derivative of the integral ends up being. So take a look at both of these equations that I have up here. Let's get rid of this ugly green t really quick. Pretty close. All right, let me change those into x's, or t's. I mean, sorry, don't wanna, so I got rid of them in the first place. There we go. So that's a t, right? Okay. So look at this. So here's my original equation, 3t squared, right? So using the second part of the fundamental theorem of calculus, I can just evaluate that function at my bound. So this is going to be, I guess I could, well, yeah, I'll write it up here. I'll write it here in the middle. 3, get rid of the t, replace it with x cubed, and square it, minus, times the derivative of the inside, so times the derivative of the inside, so that's going to be 3x squared, minus this with the bottom bound plugged in, so I plug in 1, so I get 3 times 1 squared, times the derivative of that bound. Well, the derivative of 1 is 0, so times by 0. And when I simplify this, this goes away, that's equal to 0, and I'm left with my answer that I have down here. And then you could simplify this. You could actually square this out, so it becomes 3x to the 6th times 3x squared, so it's going to be, what, 9x to the 8th power will be your simplified answer. I just wanted to leave it like this so you could see this piece right here, how we go from here, the derivative of the integral, all the way down to our final answer. So same thing over here. You can tell that I plugged x cubed in for t squared times the derivative of my bound, 3x squared, and since my bottom bound is a constant, I know I'm just going to be subtracting 0 and giving me my final answer. All right, so let me try one more problem. I've written the kind of condensed version of that second fundamental theorem of calculus up here. All right, let's try it one more. So if I had the integral from, let's do e to the x to 5x. And let's say our integrand is going to be, I don't know, sine cubed of t dt, just making something up. And I wanted to take the derivative of this with respect to my variable that's in the bounds here, so derivative with respect to x. Well, instead of finding the antiderivative of this, all I have to do is follow the second fundamental theorem of calculus. Remember, this is only when you're taking the derivative of an integral, not just when you're doing an integral, it's when you're taking the derivative of the integral. So we're going to have sine cubed of 5x times the derivative of 5x, which is 5, minus sine cubed of my bottom bound, e to the x, times the derivative of that bound, which is e to the x. And that's your answer right there. Okay, I want to do one final problem, actually two final problems here. This problem here comes from an actual AP exam. This is from the 2014 exam. This is problem 3, parts A and B. I want to take a look at this. So it says the function f is defined on the closed interval -5 to 4. So from here, -5 to 4. This is a graph of f. The graph of f consists of 3 line segments and is shown in the figure above, or in this case, the figure to the right. Let g be the function defined by g of x equals the integral from -3 to x of f of t dt. Now, part A is not going to use the second fundamental theorem of calculus. I just wanted to use part A so you can see that it's okay to have a variable in the bounds of your integral. So let's try part A. It says find g of 3. So we've got part A. Here we go. So g of x is equal to the integral from -3 to whatever our x value is of our equation here, f of t, or of our function. So we want to figure out what g of 3 is. Well, I plug 3 in for x, so over here I plug it also in for x. And we got f of t dt. Do you see how this could have been a problem if we had x values here as well? I don't want those to change to 3's. I only want the bound to change to 3's. So we've got this equation here. So it says the integral from -3 to 3 of f of t dt. Now, if you recall, there are 2 different ways of solving this problem. The first way of doing it would be to use the fundamental theorem of calculus. So we could actually find if we could find the antiderivative of f, evaluated it at the top bound, and then subtract the antiderivative of little f, evaluated at the bottom bound. That is using the fundamental theorem of calculus. Now, if you look at this equation, I don't know what f is. Now, granted, they are straight lines, which could make it nice. You know, we could figure out some things and whatnot, but it would be a lot of work. So let's just, for our purposes for this problem, just say we can't figure out what the antiderivative is. The other way of solving a definite integral problem, all this means is if we have a graph of f, so let me just draw a quick little sketch here. So from -3 to 3, and if our f function, well, I guess we can draw it, actually looks like this, right? So it looks something like, like that or whatever, okay? This is saying, hey, what is the area between the curve and the x-axis from -3, actually let's do this, -3 to 3, with values, since I'm integrating from left to right, okay, my integration is going left to right, that means values above the x-axis are going to be positive, values below the x-axis are going to be negative, so right in here we're going to have negative values, right? Anyways, I find that value. I get the same answer either way. Well, with the information that we've been given, this one's going to be the better way. So as I look at my graph of f, I'm going from -3 to 3, so -3 is actually right here, so I kind of drew it wrong on this, but that's okay. Here's -3 right here. And we are going to +3, so right 1, 2, 3, okay? So this is going to count as positive value. We can just find the area of that triangle, or you could cut it into 2 triangles, that'd be just fine. And that's going to be positive. And then this little piece right here, okay, is going to be negative. So let's see, up here, this piece, this is a triangle 1, 2, 3, 4. It is a base of 5. Here's the height of the triangle here. So it's 5 by 1, 2, 3, 4. So that's 20 total. Cut in half is 10. So that value is 10. This value right here, we got a width of 1. The height sure looks like it's going to be 2. So 1 times 2 is 2. Cut in half is 1. So I've got 10 plus a -1 will give me 9. So g of 3 is equal to 9. Now notice we didn't use the second fundamental theorem of calculus on there. We were not taking the derivative of an integral, but it's good to see that you can actually have variables in the bounds, and it's just fine. It just my function here, g, is just based on how far over I go. In this case, I went over to all the way up to an x value of 3. I could change this to a 0 and only go to 0, and my output there is my output for 0, my function g, which is kind of neat. So just remember, you can solve it either of those 2 ways, whichever one is more applicable to the situation that you've been given. So now let's take a look at part B. I'm going to go ahead and erase this. All right, so part B says, on what open intervals contained in -5 to 4, so it looks like we're going from the whole thing, -5 all the way to 4, is the graph of G both increasing and concave down? Give a reason for your answer. Well, a function G, or an equation G, will be increasing when, so it will be increasing, I should say G is increasing when G prime is positive, and G is, we want concave down when the second derivative, G double prime, is negative. So that's what we're looking for. We want to know, hey, when is G prime positive, when is G double prime negative? So let's take a look at this. Here's G of x. Let's find the first derivative of this. -3x f of t dt. So I'm going to take the derivative of both sides. The derivative of G of x is going to be G prime of x. And then I am taking the derivative of an integral. That is our second fundamental theorem of calculus. So all I have to do is plug, I don't have to know what the antiderivative of f is. All I have to do is plug in my bound into my equation. So it's going to be f of x times the derivative of that bound, which is 1 in this case, minus the bottom bound plugged in, f of -3, times the derivative of that bound, which is 0. So G prime of x is actually equal to f of x. G is the antiderivative of f, and therefore f is the same thing as G prime. Now we'll come back to that in just a second. While we're at it, let's take the second derivative. So G double prime of x is going to be equal to the derivative of f. So f prime of x. All right, so now we want to know, when is G prime positive? Well, G prime will be positive anytime that f is positive. So G prime is positive anytime our graph of f is positive above the x-axis, which happens here, which happens here, and which happens here. So from -5 to 2, I guess excluding -3 and kind of excluding 2 as well, our graph is positive. There's 0 at that place, right? Well, when is G prime going to be negative? That's when our concave down. G prime is negative. Well, G prime is the same thing as the derivative of f. So here is f. Its derivative is going to be talking about slopes. So when are the slopes of f negative? So when is f prime negative? That's when the slopes of f are negative. So they are negative right here. They are negative all the way from here, all the way down to there. And so the question asks, on what open intervals is the graph of G both increasing and concave down? That happens where I've got both of these things happening. I've got -5 to 1 to -3 from 0 to 2. So there's an example of how you would use the second fundamental theorem of calculus using a graph instead of just an equation.